Hello and welcome to this research seminar talk on the threshold of spread out contact process percolation. So this is me, Balázs Ráth, and I would like to talk about some recent work with my colleague from Groningen, Daniel Valesin. This is a talk which is aimed at master's students in probability theory and PhD students in probability theory. So if you do not know what is percolation or you do not know what the contact process is, don't worry, I will try to define both of these things in the talk. However, I will also talk about this recent work and some open questions. So let me begin with the first thing, which is Bernoulli percolation. So imagine that ZD, so the d-dimensional space where the coordinates are all integers, and we also assume that dimension is greater than equal to 2. So imagine these points in the space as vertices of a graph, and the edges of this graph are just the nearest neighbor edges. So if there are 2 points in the lattice which are nearest neighbor, we put an edge between them. So this is a graph with infinitely many vertices, and this is what we call the d-dimensional lattice. And Bernoulli percolation, or percolation in general, is about the connectivity properties of random subgraphs of this graph. Namely, what we are going to do is we are going to consider a random subset of ZD, so a random subset of the vertices, and we are going to look at the subgraph spanned by this random subset of vertices. So here is some notation. I want to phrase things not in terms of this random subset B, but in terms of the indicator of this set, which we are going to denote by Xi. And Xi is a configuration of zeros and ones on ZD. So to each point of ZD, we are going to assign 1 if that point is in the set B. So if a vertex X is in B, then the corresponding value Xi of X is going to be 1, and in this case we are going to say that this vertex is occupied, while if the vertex X is not in the set B, then I'm going to say that Xi of X is 0, or alternatively I'm going to say that this site is vacant. So this configuration of zeros and ones Xi encodes this subset B of vertices. And since we want to talk about Bernoulli percolation, the way I'm going to generate this random subset B is the easiest imaginable way. I'm just going to include every vertex X independently from the others with probability P. So this is what I'm going to call Bernoulli percolation. And I'm going to denote this, the distribution, the law of this random configuration of zeros and ones by pi underscore P, where P denotes the density. And again, this is going to be, these are IID random variables, so these random variables Xi are IID with Bernoulli distribution with parameter P. And this is how I choose my random subset of the lattice, and I'm going to be curious about the connectivity properties of this subgraph that is spanned by this random subset B. Namely, the most important thing that I will be interested in is whether this subgraph contains a connected component with infinite cardinality. So if you have, so of course ZD is connected, but now if I look at this random subset B, then it's going to have many connected components, and I'm going to define an event called the percolation event, which is of course an event on this probability space. So this percolation event is just a subset of possible configuration, namely the percolation event consists of those configurations of zeros and ones for which there exists a nearest neighbor path in ZD, x1, x2, x3, and so on. These are the vertices of this path. So if this is a nearest neighbor path in ZD, such that for all values of I, if you look at site xi, then its xi value is going to be equal to 1. So if it's occupied, if there is a path such that all of the vertices of this path are occupied, then I say that this configuration is in the percolation event, so percolation occurs. By the way, the word percolation means the flow of some sort of liquid. So imagine that if all of these sites are open, and if you open a water tap at location x1, then the water can percolate, the water can flow on this open path all the way to infinity. So this is the percolation event, and this is the random configuration that we choose. Once again, with probability p, a site is occupied, and with probability 1 minus p, a site is vacant. And here's a classical theorem that dates back to the mid-20th century, and it goes like this. There is a phase transition. There exists a critical threshold value, which we call PC, the critical probability, which is strictly between 0 and 1, such that if the density of the Bernoulli percolation, the density of this random subset, is strictly smaller than P, then the probability under our probability measure, the probability of the percolation event is 0. This is called the subcritical phase. This is the case when we say that percolation does not occur. So if P is less than PC, then all of the connected components of the subgraph spanned by this random subsets, all of these connected components are going to be finite. On the other hand, if P is greater than PC, so if the density is big enough, then the probability under the product Bernoulli measure, the probability of the percolation event is equal to 1. This is what we call the supercritical phase. This is, we also say that percolation occurs, and with probability 1, there exists an infinite connected component in the subgraph spanned by this random subset of vertices. So this is very funny. This is a phase transition because you change P continuously, but the probability of the percolation event jumps from 0 to 1 as soon as P crosses this critical threshold PC. So this was a quick recap of Bernoulli percolation that you may have already heard about. But this talk is really going to be about percolation, but percolation in a completely different model where sites are kept in a correlated way. So it's not Bernoulli percolation that I want to talk about, but it's a percolation configuration obtained in the following way. So let's talk about the next ingredient of this talk, which is the contact process. So the contact process also was invented somewhere around the middle of the 20th century, and it's an interacting particle system. So it's going to be a continuous time Markov process where the state space is the configuration of zeros and ones on ZD. And this process is also going to have a parameter lambda. So we are going to discuss what the contact process is with infection rate lambda. And the notation is as follows. So for every value of t, xi t is going to be a configuration of zeros and ones. So this is the state of my Markov process at time t. And this has the following interpretation. We are going to, so at time t, if you look at vertex x, and if xi tx is equal to 1, then we say that this vertex is infected, while if xi t of x is equal to 0, then we say that the vertex x is healthy at time t. So this is these are going to change over time. Healthy individuals can become infected, then they can become healthy again, and this can go back and forth. So this contact process is a model of a disease for which there is no immunity. So healthy individuals can become infected, they can become healthy again, and back and forth. They can catch the disease again and again through as time progresses. And now let me define the dynamics of this Markov process. It's actually very simple and natural. If you're infected, then you heal at rate 1. Namely, so what this means is that if there is an individual so if there is an x is a vertex in ZD, and x, you think about a person sitting at location x. So this person, if he is infected, then there is an exponential clock with rate 1, and when that clock rings, this guy becomes healthy. And of course, this recovery clock is independent for all infected individuals. So this is one part of the dynamics. Infected people, independently from each other, they are going to heal at rate 1. Now let's discuss how healthy people catch the disease. If there is an infected site, then this site infects each of its healthy neighbors at rate lambda divided by 2d. So the reason for this parametrization is as follows. Of course, we are on ZD, and this is we discussed the nearest neighbor lattice, meaning that each individual has 2d neighbors. So if an individual infects each of its healthy neighbors at rate lambda divided by 2d, then that means the following thing. So if I'm infected, then again I have a different clock. Now I also have an infection, so I have an infection clock with me, and the rate of this exponential clock is lambda. When my infection clock rings, then I choose one of my neighbors uniformly at random, and I try to infect this other person. If that other person is not infected at the time when I try to infect him, then he will become infected, and if he was already infected, then nothing happens. So that's how the infection spreads. Infection spreads in a random way from sites to neighboring sites. And so one way of saying this is that I have an infection clock with rate lambda, and then I choose a random neighbor and infect it with so when the clock rings, I choose a uniform neighbor and I infect it. Or I can alternatively say that on each of the edges that point from me to my neighbors, I have an infection clock of rate lambda divided by 2d, and if any of these clock rings, then then I'm going to transmit the infection on the arrow whose along the arrow whose clock just rang. So these are two different ways of saying the same thing, and this is the definition of the contact process. Infected sites heal at rate 1, and if a site is infected, then it's going to infect each of its healthy neighbors at rate lambda divided by 2d. That's it. This is the definition of the contact process. At first, it might look strange that this is a Markov process with an infinite state space, since the state space is the configuration of zeros and ones on ZB. But this this makes very good sense. This is a well-defined object, and that's a classical thing. But now that we defined the contact process, the main question that we want to study is epidemics. So if I have a contact process with infection rate lambda, is there going to be an epidemic or not? And one way of phrasing this is talking about stationary distributions of this Markov chain. Namely, a stationary distribution of a Markov chain is a random configuration of zeros and ones, such that if you run the Markov process with this initial state, then at any time t, the distribution of the configuration of infected sites is going to have the same distribution as the one that you started from at time 0. So the question is there a stationary distribution where the density of infected sites is positive? And the answer depends on the value of lambda, the value of the infection rate. There's a theorem that, again, some sort of phase transition occurs. So there exists a positive but finite threshold, the critical infection parameter lambda c, such that if the value of lambda is less than or equal than lambda c, then the infection goes away, the infection dies out, the infection rate is not big enough to maintain a global epidemic, meaning that the only stationary distribution is the state where every single person is healthy. This is called the subcritical phase, but actually if lambda is equal to lambda c, then still this is a highly non-trivial theorem by Grimet and Bizudenhout, is that even if lambda is equal to lambda c, then still the only stationary distribution is the trivial one where every single person is healthy. Maybe I forgot to mention, of course, if everyone is healthy, then the contact process stays, then everyone stays healthy because there is no one to spread the infection. And of course, this is this state when everyone is healthy is of course a sink of this Markov chain. Once you hit this state, then there is no escape from it. Okay, so that was the subcritical phase, but the important part is that if the infection rate is bigger than this critical value lambda c, then something else happens. Of course, the trivial stationary state is still there, but there exists another stationary state. So there exists a stationary distribution of this Markov chain that we denote by mu lambda, where the density of infected sites is positive. So somehow there exists a different state where there are infinitely many infected guys, and if you run the contact process, so if you run this dynamics of infection, then these guys keep on reinfecting each other, so that this global epidemic on average stays as it is. So this is kind of a depressing thing, but in this model this can happen, that the infection never goes away. This is because there is no immunity, and in the supercritical phase of the contact process, so if the infection rate is big enough, big enough, this is what happens. And the theory also says that actually in the supercritical phase there is only one. So there is the trivial stationary distribution where everyone is healthy, and there is a unique other stationary distribution, and this is what we call the upper invariant measure. The reason why it's called upper invariant measure is that the easiest way of obtaining this stationary measure is by starting from an initial configuration when everyone is infected, and if you run the contact process starting from this initial state, and if the lambda is bigger than supercritical, then as t goes to infinity, as time goes to infinity, the law of this configuration is going to converge to the upper invariant measure. So this is well-known concept of convergence to stationarity in Markov chains, and it does happen here, especially if you start from the state where everyone is infected. But if lambda is less than or equal than the critical threshold, so if the infection parameter is small enough, and if you start from the state where everyone is infected and you run time, then the infection will kind of go away. It's the density of infected sites is going to go to 0 as t goes to infinity, and therefore the upper invariant measure in the subcritical phase is just equal to the trivial state where everyone is healthy. So this is the phase transition of the contact process. And there is one thing that I would like to stress about the stationary measure of the contact process, the upper invariant measure. So this is also a probability distribution on the configurations of zeros and ones on ZD. This is a random state, quite similarly to the Bernoulli percolation, which was also a random configuration of zeros and ones. It's just now we call ones infected and zeros healthy, and as opposed to Bernoulli percolation where we called the ones occupied and the zeros vacant. But this mu lambda, this is a measure, this is a probability distribution on configurations of zeros and ones. However, this upper invariant measure, this is not Bernoulli percolation. Sites under the invariant measure are not independent. If you're infected in the stationary state, that makes it more likely that your neighbor is also infected. So under the stationary distribution, there are correlations, and as a matter of fact, this random measure is positively associated, meaning, well, it's a generalization of this fact that if you look at the status of a vertex and you see that it's infected, then this event is going to make it more likely that other people will be infected. So this is a generalization of this property is called positively associated. So the correlations under this measure are positive, and therefore you can imagine that the set of occupied sites or the set of infected sites will have a tendency to be clustered. That if there is if someone is infected, then there is going to be a group of infected people around him. And this and also let me mention kind of a simple property, so which involves the notion of stochastic domination. So I just want to say that if there are two possible infection parameters, lambda 1 and lambda 2, and if you look at the upper invariant measure, of the contact process corresponding to the infection parameter lambda 1, then this is going to be stochastically dominated by the upper invariant measure corresponding to the infection parameter lambda 2. Well, intuitively this is clear. If the infection parameter is bigger, then there are going to be more infected people under the invariant measure. So let me remind you, because I want to talk about percolation again, but now I want to look at the percolation of infected sites under the upper invariant measure of the contact process. So let me remind you that the definition of the percolation event, so this is just a configuration of zeros and ones, psi, is in the percolation event if there is an infinite nearest neighbor path of sites which are all occupied. Or, in the language of contact process, they are all infected. And then here's a result which is not very deep. So let's look at the stationary distribution of the contact process let's look at it as a correlated percolation model on ZD, and again let's assume that the dimension is greater than or equal to 2. So here's a theorem which is quite simple to prove. Namely, there is going to exist again a critical threshold that I denote by lambda p. So this is the percolation threshold which is different than lambda c. So if you remember, lambda c was the lowest value of the infection parameter lambda, such that well, if lambda is strictly greater than lambda c, then there is a non-trivial upper invariant measure. But now I want to define a different critical threshold, namely there is this percolation threshold that if the infection rate is strictly less than this lambda p, then under the upper invariant measure corresponding to this lambda, percolation occurs with 0 probability, so all of the connected components of infected sites is going to be finite with probability 1. So the percolation event has probability 0, but if lambda is strictly bigger than lambda p, then percolation occurs. So the set of infected sites percolates. There is going to be an infinite connected, nearest neighbor, infinite connected component of infected sites with probability 1. And this is an easy fact. The fact that this probability of the percolation event jumps from 0 to 1, this is easy because of the previously mentioned stochastic domination, and you have to combine it with this so-called the property of ergodicity with respect to spatial shifts of the upper invariant measure. Namely, if there is an event which like the percolation event, which is invariant under spatial shifts, then the probability of this event under the upper invariant measure has to be equal to 0 or 1. So the fact that there exists such a lambda p is kind of a triviality, and it's also trivial to see that lambda p has to be greater than lambda c, because of course if lambda is strictly less than lambda c, then the upper invariant measure consists of all zeros. Everyone is healthy. So in that case, of course, there is no percolation because we are talking about the empty graph, and of course the empty graph does not contain an infinite connected component. So that it's a triviality that lambda p is greater than or equal to lambda c. What is non-trivial is whether lambda p is finite or not. And here's a theorem by Tom Liggett and Jeff Steiff from 2006. So what they prove is that lambda p is finite. So what they prove is that if you make the infection rate lambda big enough, then, and you look at the upper invariant measure of the contact process with rate lambda, then it's going to percolate with probability 1 if lambda is big enough. And the proof goes like this. Well, okay, it's a very sketchy sketch. Namely, what they actually prove is that no matter how you choose a density between 0 and 1, and think about q being very close to 1. So no matter how you choose your density, no matter how close that density it is to 1, there exists an infection parameter big enough such that the upper invariant measure of the contact process is going to stochastically dominate a Bernoulli product measure with density q. And so the upper invariant measure dominates a product Bernoulli measure with density q. And as soon as you prove this, you're done, because you just choose q to be bigger than the Bernoulli side percolation threshold that we defined on the first slide. So if q is bigger than pc, and then you choose lambda accordingly, then the upper invariant measure dominates the Bernoulli configuration with density q. But since the Bernoulli percolation with density q has an infinite component, therefore something that stochastically dominates it also has an infinite component. Therefore, under the so the stationary, the upper invariant measure, the upper invariant configuration of contact process with infection rate lambda is also going to percolate. But of course, the main result, or one of the main results of this paper of Liggett and Steiff, is this stochastic domination result. And then the fact that the conclusion about percolation is just automatic. But here is the big open question which is posed by Liggett and Steiff. Do we have lambda p strictly bigger than lambda c? So let me go back to my previous slide. So if you remember, lambda c was the critical threshold of the contact process. So if lambda is less than lambda c, then the upper invariant measure is trivial. It consists of healthy guys. Everyone is healthy. And if lambda is bigger than lambda c, then there is a non-trivial upper invariant measure. But the question is, if strict, and of course the percolation threshold, so the lowest value of lambda above which you have percolation in the above which you have percolation is a different threshold. And the question is, are these two thresholds different? So can you choose, the question is, can you choose a lambda for which there is an epidemic, for which the upper invariant measure is non-trivial, yet it does not percolate? It only has finite connected components. So this is a question which is open. They posed it in 2006, and we did not solve this open question. So this question is still open up to this day, but this did not stop people from investigating the values of lambda which are between lambda p and lambda c. Namely, people have written papers about the sharpness of the percolation phase transition. So what people proved, namely in 2008 Rob van den Berg, and in 2018 Thomas Bekenkamp, what they proved is that if you take any infection parameter which is strictly smaller than this percolation threshold, then the connected components are very small. The connected components in the subgraph spend by infected sites is going to be very small. So if you look at the connected component in the upper invariant, so if you look at the infected connected component of the origin under the upper invariant measure, so the probability that the cardinality of this connected component is greater than equal to n, this is going to decay exponentially as n goes to infinity. This is a different way of saying that connected components are small. This is what we call sharpness of phase transition. So so like this change in the phase transition is really drastic, because if lambda is less than lambda p, then connected components are kind of small, so their size decays exponentially. But as soon as lambda is greater than lambda p, then of course there is an infinite component, which is completely different. So sharpness of phase transition has been proved in dimension 2 by Rob van den Berg, and for any dimension greater than equal to 2 by Thomas Bekenkamp. So these are nice results. However, let me point out the potential absurdity of these results, because if this open question is answered in the negative, so if it turns out that lambda p is equal to lambda c, then the results become a triviality, because for any lambda less than lambda c, we talk about the empty configuration, and of course then the connected component of any vertex has size 0. So this is strange, but this also shows that people strongly conjecture that these two critical thresholds are not equal. That's why people talk about, that's why people prove results which are only meaningful if the value of lambda is strictly between these two values. So this is an open question, and this open question motivated our work with Daniel. But we could not solve this open question, but we do solve something which is relevant. So, but in order to state our result with Daniel, I have to modify the definition of the contact process. Namely, I want to define the contact process on the d-dimensional lattice, which has infection rate lambda, but now I want my contact process to have range R. And here it goes. We still talk about a continuous time Markov process on ZD. So each person on ZD can be either healthy or infected. But now you're going to spread the infection not only to your nearest neighbors, but you're going to be able to spread the infection in a ball of radius r. So let me try to define the spread out contact process with the infection rate lambda and range r. The healing procedure is just the same as before. Infected sites heal at rate 1. So if I'm infected, then I have an exponential clock with rate 1, and when that clock rings, I become healthy again. But the infection dynamics is a little bit different. So if I'm an infected site, then I have an exponential clock with rate lambda, and when that clock rings, I'm going to pick a vertex uniformly from a ball of radius capital R around the vertex X. So when my clock rings, I pick a random vertex from this ball, and I'm going to try to infect it, unless it's already infected, in which case nothing happens. So in the old model, I picked a uniform neighbor, a uniform nearest neighbor, but in this model, this infection is a bit more nasty, because now it's airborne. So like if you sneeze into the air, then the infection can travel up to distance capital R. So this is my new model. This is called the spread out contact process. and we will be able to state results when the value of R is very big. And okay, so here is one more thing. So I did not really specify what kind of ball I'm thinking about. Of course, this is going to be a ball inside ZD, so I will only be able to infect other guys whose coordinates are integers. And more specifically, I'm going to talk about so in our paper, for technical reasons, we use balls with respect to the L infinity norm. So actually these balls are actually boxes, because of course a ball with respect to the infinity norm looks like a box. But of course it would our results would hold equally well if we choose another norm, let's say the Euclidean one. It's just the proof is the easiest if you choose the L infinity norm. Okay, so this is my new definition of so this is the definition of the spread out contact process, which now has two parameters, the infection rate lambda and the range R. However, I can still define the critical threshold lambda C. So this is the parameter lambda, such that if you're above this, then the upper invariant measure is non-trivial. So there is a non-trivial epidemic stationary state with positive fraction of infected sites if the infection parameter is above this lambda C, which now depends on R. And let me also define the analog of the percolation parameter. So lambda PR is going to be the critical threshold above this. So if the infection rate is bigger than this, then you can observe percolation. So if lambda is bigger than this, and if you look at the upper invariant measure, if you look at the configuration of infected sites with upper invariant measure, then it's going to set under this in this configuration with probability 1, you will see that the percolation event occurs. You will see that there is going to be a connected component of infected sites which has infinite cardinality. So you can define these two thresholds, and our result is going to be about the relation. Well, it's going to be about the asymptotic behavior of lambda p when the range R is very big. But before that, I want to talk about the asymptotic behavior of the critical threshold lambda CR when R is very big. So this is a known result. This was proved in 1989 by Bramson, Darrett, and Swindle, that of course the dimension is fixed. So now I'm on ZD, where D is some fixed number. Let's say the two-dimensional space or the three-dimensional space. So dimension is fixed, but if you look at how the critical threshold of the contact process behaves as R goes to infinity, what you will see is that this converges to 1. And actually their main result is more precise than this, because they even identify the rate of convergence, the speed at which it converges to 1. And that convergence rate depends on the dimension. But for this talk, I will only need this result. So actually, what they also prove, and that's going to be important for us, if oh, by the way, sorry, before I go on saying what this means, it means that if the infection rate is strictly bigger than 1, then there exists a range big enough so that if the range of the contact process is bigger than that R0, then the upper invariant measure is going to be non-trivial. But on the other hand, if you take any lambda which is strictly less than 1, and if you take the range big enough, then the upper invariant measure is going to be trivial. So the upper invariant measure consists of all of the the upper invariant measure is concentrated on the configuration where everyone is healthy. So what they also prove, Bramson, Darrett, and Swindle, is that if lambda is strictly bigger than 1, then they even identify as r goes to infinity, as the range goes to infinity, they even identify the asymptotic density of infected sites under the upper invariant measure. So the asymptotic density of infected sites is of course equal to the probability that, so the probability under the upper invariant measure that the origin is occupied, that is just the same as the density of infected sites under the upper invariant measure, because every site looks the same. So the probability that one guy is infected is the same as the density of guys who are infected. And what they show is that as r goes to infinity, this thing converges to 1 minus 1 over lambda, which is, for simplicity, we are going to denote this by sigma lambda. Note that this sigma lambda is positive if and only if lambda is strictly greater than 1. So if lambda is greater than 1, then asymptotically the density of infected sites under the upper invariant measure is going to be this positive number, sigma lambda. And by the way, this the reason why there is an explicit formula for this when r goes to infinity is that this sigma lambda, this is just the survival probability of a branching process which has birth rate lambda and death rate 1. So this is of course a continuous time branching process, but the branching process goes like this. If I'm alive at the current generation, then I have two competing clocks. One has rate 1, and if that clock rings, then I die. So but of course this is from the point of view of infection. So this is at rate 1, the infection dies. So this infected individual disappears. But also I have another clock, the infection clock, which has rate lambda, and if that rings, then I produce an offspring, namely I produce with rate lambda another infected person. So this is the branching process. And what the meaning of the message of their theorem is that if the infection radius is big enough, then the infection spreads essentially in a similar way as a branching process, because of course for any finite value of r, you're in ZD, so so the geometry matters. But if r is very big, then essentially when you infect someone, that person is so far away from you that you can treat that there is no effect. So you can essentially model things by a branching process. So that is the heuristics. That's why this limiting density is just the survival probability of the branching process. Well, I should have mentioned this, and this is going to become clear from things that I will say later, that this probability, so the probability that the probability that under the upper invariant measure you're occupied, we will see that this probability is the same as the probability that if you start from one single infected site from at the origin, everyone is healthy, then the probability that you create an epidemic that never stops, that an epidemic that will go on forever, the probability of that event is equal to this quantity for any value of lambda and r. So that's something that I will describe later, but that's why the things are related to the survival probability of a branching process. And there is one more thing that one can prove, but actually this is not proved in the paper of Bramson, Darrett, and Swindle, and this would come out of the methods of the paper that I'm going to talk about. So what one can prove is that the upper invariant measure converges weakly to the Bernoulli product measure with this density lambda. So lambda is fixed, but r goes to infinity. Then this weak convergence means that if you choose r to be very big, then the configuration under the upper invariant measure, it's going to look like locally very much like IID. So if you choose any k and any fixed number of k, no matter how big it is, let's say 100, but you fix the number k, and if you look at k sites of ZD, k vertices of the graph, but you let r go to infinity, then the joint distribution of the occupancy of these sites under the upper invariant measure, it's going to converge as r goes to infinity to IID with this probability. So this is weak convergence or local convergence of this configuration to the product Bernoulli configuration. And then, given this, it's not very surprising that we have the following result. So here is the main result of our paper, finally. It says that if you look at the percolation threshold of the upper invariant measure, then this percolation threshold converges to some limit as r goes to infinity. Quite similarly to the result above, just the value is different. So this is equal to 1 over 1 minus PC, where, reminder, PC is the Bernoulli percolation threshold of ZD, the Bernoulli nearest neighbor site percolation threshold of ZD. And of course, this number, since PC is strictly less than 1, this 1 over 1 minus PC is finite, and since PC is bigger than 0, this 1 over 1 minus PC is a number which is bigger than 1. So this limit is a number which is strictly bigger than 1, but strictly finite. And okay, so this formula looks magical, but it's not going to look that magical as soon as one notes that this. So if you look at a branching process whose infection rate is smaller than this, then the density corresponding to that, or the survival probability corresponding to that. So, okay, how should I put this? So if the infection rate is smaller than this, then the density of infected sites in the asymptotically, when r goes to infinity, the density is going to be less than PC, and if the infection rate is bigger than this, then asymptotically, due to this formula, the density is going to be bigger than PC. So it's kind of heuristically clear that since these measures converge locally to Bernoulli product measure, it makes sense that the critical threshold, the infection threshold, converges in a way that as soon as the density of infected sites under the upper invariant measure is bigger than PC, you will percolate, but if it's asymptotically smaller than PC, then you will not percolate. So now I made my result, or our result, with Daniel sound a bit trivial, but let me try to argue that our result is not that trivial after all, because it's kind of easy to prove. It's not very hard to prove weak convergence of the upper invariant measure as r goes to infinity to Bernoulli product measure with this density rho lambda. So this is easy, but our result, the percolation result, does not follow from this. So our result is not a consequence of this weak convergence. And the message here, so the moral of the story, let me say the moral of the story immediately. So weak convergence is a local property, but percolation is a global property because so weak convergence is phrased in terms of the joint distribution of finitely many sites, let's say 100, but in order to even to define or to talk about the percolation event, you have to talk about the occupancy of many sites, infinitely many sites. But actually, here's a mathematical result that shows that things are not as easy as they look. Namely, just because if something locally looks like a Bernoulli configuration, it does not necessarily behave like a Bernoulli percolation globally. Namely, for any density and for any finite value of k, you can create a measure on the set of configurations of zeros and ones such that for any finite subset of ZB for whose cardinality is less than k, if you look at the joint distribution of the occupancies of the sites inside this set H under this measure, it's going to look like Bernoulli product measure. However, this measure is not Bernoulli product measure, despite of the fact that if you look at only the joint distribution of k sites, it looks like Bernoulli percolation. Nevertheless, it's different to the extent that it does not, you can prescribe such a measure such that it percolates, or you can prescribe such a measure such that it does not percolate. So my point is that this happens for any density. So if you know, if I tell you, well, I have a measure whose density is B, and if you restrict it to sites, if you only look at this measure or the law of this measure for fixed at most k sites, it looks like a Bernoulli measure. Still, you will not be able to make a conclusion whether it percolates or not, because you can create such a measure which percolates, and you can create such a measure which does not percolate. So again, the message is weak convergence is a local property and percolation is a global property. So in order to prove our theorem, we have to do some extra work. It's not enough to show weak convergence. We have to show something stronger. And here's another remark. So how we prove this theorem. If you remember, Liggett and Steiff proved their result using stochastic domination. So what they did was they globally dominated, well, okay, not really dominated, but minorated the upper invariant measure with a Bernoulli measure. But let me say it immediately that our proof does not work like this. We cannot dominate or minorate these upper invariant measures in a way with Bernoulli measure in a way that will give us our result. So this is an open question. The question is it true that for any value of lambda and for any epsilon, is it true that if you make the range of the contact process big enough, is it true that you can stochastically dominate or minorate the upper invariant measure with the Bernoulli product measure whose density is only a little bit bigger or only a little bit smaller than the density of occupied sites under the upper invariant measure? And of course, if if R is big enough, then we know that the density of occupied sites here, it's going to be somewhere near sigma. But stochastic domination is a different thing. So can you really couple the upper invariant measure to a Bernoulli measure such that it's simply bigger? And this is an open question. We do not know if this is true or not. We certainly do not know how to prove this result. But let me stress, as soon as this result would hold, this would immediately imply our result. And our paper is very long. It's like 60 pages. So it would be pretty upsetting for us if this open question would have an easy, simple answer, because that would eliminate our paper. But still, I wanted to stress that this open question is out there. So the open question is like, can you, if range is big enough, can you sandwich your upper invariant measure in between Bernoulli product measures, which are whose density is quite close to each other? So this is the open question, but now let me mention a corollary of our theorem. Namely, our theorem has some relevance to the open question posed by Liggett and Steiff. But we cannot resolve the open question in the nearest neighbor contact process. We can only resolve that open question if the range is big enough. Namely, by the result of Bramson, Darrett, and Swindle, as R goes to infinity, this lambda c converges to 1, and our result with Daniel is that this other sequence converges to a value which is strictly bigger than 1. Therefore, as a corollary, you obtain that if R is big enough, then these two values, these two critical values, are different. So this was the open question of Liggett and Steiff. The two thresholds are different, and this holds for any value of d greater than equal to 2. So this is a reason to celebrate, because this can be viewed as a step in the direction of the proof of Liggett and Steiff. So this is a valuable result, but again, let me mention a remark that was made to us by Stein, Bertelsen. Namely, actually, if you only aim for this conclusion, that lambda PR is greater than lambda CR, if R is large enough, then actually there is kind of a trivial argument for that if the dimension is equal to 2. But here's a simple proof of just this conclusion. So this is very restricted argument because it only works for d equals 2, and it does not prove the asymptotics. It just proves that the strict inequality holds if the radius is big enough. So here's the argument. It's kind of silly. There is a very trivial way of upper bounding the upper invariant measure by a Bernoulli product measure with value lambda divided by 1 plus lambda. So remember, the result of Liggett and Steiff was that upper invariant measure dominates Bernoulli measure, but there is a and that's a non-trivial result. So the result of Liggett and Steiff is hard, but there is a super trivial argument that I'm not going to recall now, that the upper invariant measure for any value of lambda and r, it can be stochastically dominated by, so this time it's the Bernoulli that dominates, and the parameter of that Bernoulli is lambda divided by 1 plus lambda. So the argument is explained in our paper, and it's 2 lines, but I don't have time to explain it now. But as soon as you believe that this holds, and of course you have already believed me when I told you the result of Bramson, Darrett, and Swindle, namely that when r goes to infinity, then the critical threshold is 1. And if you put that together with the well-known fact that if dimension is 2, then the critical threshold of Bernoulli percolation, Bernoulli site percolation, it's a well-known fact that that critical value is strictly bigger than 1/2. This is a classical result from the 80s. So if you put together these 3 facts, then you get the desired result. Because here's the deal. If I choose lambda to be 1 plus epsilon, where 1 plus epsilon is so small that lambda over 1 plus lambda is less than PC. So remember, if lambda is 1 plus epsilon, then this lambda divided by 1 plus lambda, this is going to be a number which is strictly bigger than 1/2, but you can make it as close to 1/2 as you wish. So you can make it small. So by making epsilon small, you can make this value lambda divided by 1 plus lambda, you can make it smaller than PC. Now, for this value of lambda, if r is big enough, then the contact process survives. That's the result of Bramson, Darrett, and Swindle, that lambda c converges to 1. So if lambda is 1 plus epsilon and r is big enough, then the contact process survives. The upper invariant measure is non-trivial, but since for this value of lambda, the upper invariant measure is dominated by a Bernoulli whose parameter is less than PC, therefore the dominating Bernoulli does not percolate, and therefore my upper invariant measure does not percolate either. So for this value of lambda, the contact process survives, but it does not percolate. Therefore the 2 critical thresholds are different because this value of lambda is between them. So this is the trivial argument of Stein. But this only works when dimension is 2. So if dimension is 3 or higher, then PC is already less than 1/2. Plus, our result with Daniel is much more precise because it gives the asymptotic value of the critical percolation threshold as the infection radius goes to infinity. So here are a couple of words about the proof of our result with Daniel. Well, it's going to, so this is my thing. So if you've seen lectures by me, then probably you know that one of my tricks is multi-scale renormalization, and this is a method that we have already used with Daniel. So this is already the 3rd paper that I co-author with Daniel. That involves multi-scale renormalization to tackle a problem in percolation. And of course, the classic Pyers argument, if you don't know what it is, it doesn't worry, but this is kind of a classical argument with which one usually proves percolation or the absence of percolation. So this is one ingredient. Another ingredient that I will talk about a little bit in this lecture is that in order to compare the upper invariant measure to a Bernoulli configuration, we are going to use a very nice coupling, a coupling of the graphical construction of the contact process, and we are going to couple it with independent branching random walks. So this is kind of natural because you want branching processes to appear, because if you remember, even in the case of Bramson, Darrett, and Swindle, somehow you understood things when r went to infinity in terms of branching processes. So it's kind of natural that branching random walks are going to pop up. And other ingredients are proof are well-known and classical results about Bernoulli percolation. that we will use to make conclusions about the percolation of the contact process. And one ingredient of our proof that I will not talk about is that actually we are going to prove a variant of the result of Liggett and Steiff. So there is a result which is in kind of the style of that Liggett and Steiff result, namely we want to lower bound the upper invariant measure with range R with product Bernoulli measure. So we actually do use a stochastic domination result, but we have to do a bit of coarse graining to be able to compare our upper invariant measure to product Bernoulli. But this is something that I will not talk about, but that's like takes up 20 pages of our paper. So what I will try to talk about is this coupling of branching random walks and the graphical construction of the contact process. So first of all, what is the graphical construction of the contact process? It looks like this. So imagine that these are the sides of ZD. So here at the bottom you have d-dimensional space, and for simplicity let me draw that dimension is equal to 1. So of course our theorems are only interesting if the dimension is greater than equal to 2, but I'm going to just draw the d equals 1 case. So how to construct the contact process? So imagine that these lines, these are times. So this is like a space-time picture where at the bottom you have time 0, and as time goes up, this is how time increases. So for any horizontal line, you will see a snapshot. So every horizontal line at height t. So if let's say the vertical coordinate. So if I draw a horizontal line whose height is t, then somehow that is going to give me the contact process at time t, and the way to do it in space-time is using infection arrows and recovery marks. So if you remember, the rule of the contact process was, whether it was nearest neighbor or spread out, was that there are these exponential clocks, and if the clock rings, then you either heal or you infect someone. So these red marks, these are called the recovery marks, and the recovery marks form a Poisson point process. On each of these lines we put a Poisson point process of recovery marks, and the rate of that Poisson point process is equal to 1. So therefore, if I start from this guy, and let's say he's infected at time 0, then the vertical coordinate of the first recovery mark that this guy is going to encounter, so the time it takes to meet the first recovery mark, that's going to have exponential distribution with rate 1. That's a well-known property of Poisson point processes, that you have to walk an exponential time with rate 1 in order to see the first recovery mark. And of course there might be other recovery marks later. And I also want to put Poisson processes of infection arrows with the appropriate rate. So infection arrows pointing to a certain neighbor are going to have the Poisson process of infection arrows will have to be lambda divided by the volume of ball of radius r. And then the next thing that happens is that if you encounter an infection arrow, that means, let's say if this guy was infected at time 0 and there's an infection arrow here, then bloop, along the infection arrow the infection spread, and now at time t, let's say this is t, this guy is also infected. So this way you can define infection paths, and let's say if this guy was infected at time 0, then for example, this was the first time when both of these guys became infected, and so on. But then there was a recovery mark, so then this guy is no longer infected. So this green part maps the trajectory along which the infection was spreading. For example, there was an infection arrow here and here and here and so on. For example, at this particular time instant, these three guys were infected if you start from this particular infected guy at the beginning. So this is the picture. These are infection paths. This is classical. But here's a little remark. Namely, one can construct the upper invariant measure using this picture. So you can use this graphical construction to construct the upper invariant measure in the following way. Let me define psi tilde tx to be the indicator that there is an infection path from x0. So you remember, infection paths are these paths in space-time. So there is a point in space-time whose space coordinate is the site x and time coordinate is 0. If there is an infection path to some site at time y, at time t, so if there is an infection path oriented upwards, of course, then I turn this indicator on. And if there is no infection path from this point in space-time to that point in space-time, then this indicator is 0. So my point is that by the self-duality of the process, this configuration has exactly the same distribution as the contact process at time t if you start it from all infected sites. This is called duality, and this is really time reversal. So if you start from all infected here, then the configuration that you see at time t here, that's the same thing as looking at those sites here at the bottom whose infection path reaches up to time t. So that's just like if you turn this picture upside down, it's easy to realize that this identity holds. So this way you can construct a configuration which has the same distribution as the contact process at time t. But then the funny thing is that in this construction, this is a decreasing sequence, because if there is an infection path up to time t, then necessarily there was an infection path up to time s for any value of s less than t. So this is a decreasing sequence. So they converge monotonically to something, and that something, that configuration, is has the distribution of the upper invariant measure. So if you look at the graphical construction, then the set of those sites whose infection path goes to infinity. So if those sites at time 0 from which there is an infection path that goes up to infinity, this set of sites have the same distribution as the upper invariant measure. So this is a fun fact. This is a very nice hands-on construction, graphical construction of the upper invariant measure. And what we want to do is we want to compare this to an IID Bernoulli configuration. Namely, what we want to do is we want to replace these infection paths. We want to replace them with branching random walks that are independent. So let's consider independent branching walks with jump range r and jump rate lambda and unit death rate, starting from all sites x in ZD. So this is a branching random walk where you wait. So you have, if you're a particle, then you have two clocks. One of them has rate lambda and the other one has rate 1. And if the death rate clock rings, then you die. And if the birth rate or jump rate clock rings, then you produce an offspring and you put that offspring in a ball of radius r uniformly. So this is a branching random walk, and I want to define a different indicator. I want to define eta tx to be the indicator that my branching random walk started from the site x, survives up to time t. And of course, this event is the same as the analogous event about a branching process. So the fact that these guys perform random walks does not really affect the fact that whether they survive or not. So actually, this configuration, since these are IID random walks, this is a Bernoulli configuration. So this is a Bernoulli configuration whose density is just this sigma lambda t, which is just the survival probability of a branching process up to time t. And of course, this converges as t goes to infinity to this value sigma lambda that we defined earlier. So if you remember, on this earlier slide, I defined sigma lambda to be the survival probability of a branching process with the birth rate lambda and death rate 1. And of course, as t goes to infinity, this converges to that value. And now what I want to do is, well, I want to recall my other indicator. So I want to, like the heuristic is that these guys, these infection paths, they look like branching random walks up to a certain time. So this other indicator was that the indicator that there is an infection path from x0 to yt. And what I want to do is, if I have a finite subset of ZD, I want to couple my branching random walks starting from this set. I want to couple my branching random walks to, I want to couple the branching random walks and the corresponding indicators to infection paths starting from the same set of vertices. And here is the deal. The point of the construction is that as long as you do not observe a particle jumping on top of another particle, then you cannot really distinguish between infection paths and branching random walks. So what you will do is at time 0, x0, so xt is going to be the subset of branching random walks that did not yet get annihilated by time t. And and of course at time 0, no annihilations occurred. And then let's say I run these branching random walks up to time t. These are the paths, the trajectories of these branching random walks. So you might see some branching, you might see some deaths, and let's say at time t you did not see any collisions. But then if you try to run it a little further, what you see is, oops, these branching random walk particles jumped on top of each other. And now in the branching random walk world, these two particles just stay on top of each other happily. But of course, this has no interpretation in terms of infection paths. So in this case, we just shut down our coupling and say that, well, these branching random walks are not really representative of the infection paths, but these other ones with the check marks, these are still okay. And then let's say I further increase t, and if I see that even starting from the same source, if particles jump on top of each other, that's not good. Then this branching random walk is no longer representative of an infection path, but still these guys are, and so on. So this was kind of a proof by picture of the following lemma. If I denote by xt the subset of those sites whose branching random walks did not yet get annihilated by t, so xt is a subset, so x0 is, so x0 is all of the set, and generally xt consists of those sites who still have a check mark. And as you can see, this xt decreases with time. For example, now these two guys got eliminated from xt, and as t increases, this further guy got eliminated by xt. So xt is the set of those starting points who did not yet get annihilated by time t, and the lemma is that for those values of starting points for which so those guys who did not yet get annihilated, for those guys, the indicator that the branching process survives up to time t is the same as the indicator that the infection path survived up to time t. So this is the indicator defined in terms of the branching random walk. This is the indicator defined in terms of the infection path, and they are the same. If x belongs to xt, where xt denotes those set of sites who did not yet get annihilated by time t. And so this is a lemma that nicely allows us to compare this configuration, which is IID Bernoulli. So this is very nice. It allows us to compare it to this other configuration that we care about, because this guy, as t goes to infinity, this will encode the upper invariant measure. So this is a nice lemma, but one has to use it with care. So if the initial set is too fat, then you will see too many annihilations immediately. So if you choose this x to be zd, or a ball with big radius, then you will see many annihilations already at the beginning, and that's not what you want. Also, since in some cases we care about the case when the branching random walk is supercritical, so the population gets bigger and bigger. So if t is too big, then you will see too many annihilations. So if the branching random walk survives, then you will sooner or later going to see such an annihilation, and that's not what you want. So these are two enemies. So I don't want to choose my set to be too fat, and I don't want to run my branching random walks for a too long time, because both of these choices will result in too many annihilations, and that's not what I want. But there is one thing that I can turn to my advantage. As long as t is fixed and as long as x is fixed, I can make the range of my branching random walks very big, and that helps, because if these branching random walks make big jumps, then very quickly they are going to be spread out in space, and they are not going to annihilate because they are so far away from each other. So that's the important thing, so that if I can make R big enough, then there are going to be few annihilations. And this is so this lemma, this coupling, can be used as an ingredient of the proof. For example, so just as a like a toy argument, let me give a sketch proof that if so I want to show that the two thresholds are big. So what I want to show is that if lambda is strictly so I want to say that for any epsilon there exists a lambda which is strictly bigger than 1, so eventually it's going to be bigger than the lambda c. I want to show that there exists a finite t and a finite range, such that I would be very happy to show that for any sets x, I want to show that if the range is big enough, I want to show that the probability that these indicators are all 1, I want to show that the joint probability is less than epsilon to the cardinality of x. So this is, as soon as I have this, my standard percolation Pyers argument would give that I'm subcritical in the percolation sense. And the way to prove this is I want to upper bound. So I want to upper bound this probability, and I chop it in two halves. One half is about my coupling, and the other half is about the properties of the branching random walk. So I want to upper bound the probability that my infection paths are well behaved. Then I want to upper bound, one way to upper bound this is I want to bound the probability that my coupling is well behaved, and I want to upper bound the probability that my branching random walks are well behaved. And the second term is very easy because my branching random walks are independent, so this sum has binomial distribution, that's easy. But the first term is tricky because I want to choose. So in order, if I remember, I want to see few annihilations. So I want to upper bound the probability that more than half of the vertices got annihilated. And of course, given lambda and given t and given x, one can choose the range very big so that there are few annihilations, but I want a bound that works for any set x. So that's hard. And we can only show this upper bound that the coupling is well behaved if the set x is very sparse, so if it's spread out in space. But that's okay, because using our renormalization, it turns out that it's enough to consider such sparse fractal-like sets. So this is the trick of renormalizations. And since it's fractal-like, there are going to be few annihilations, and our coupling works, and this probability holds. And if the way also our renormalization also gives that the number of possible choices of x is not too big, and this is how you construct this set, and this is the end of our talk. So there is no way I can explain how multiscale renormalization works in such a short talk. Well, actually the talk was already more than 90 minutes, but this is a fun tool to create fractal-like sets for which nice decorrelation inequalities can be proved. This renormalization works in very many different contexts of correlated percolation models, and this talk was one example of that. So thank you very much for the attention. Bye bye.